John Embry from the University of Virginia, and he's going to tell us about Newton's method and localization.
Well, thanks so much. I'm really grateful for an opportunity to talk here about some work that Tom Spencer and I have been working on for a couple of years now. It's been going kind of slow, but I think we have a pretty clear idea of what we're doing. It's not written up yet, so I beg your forgiveness for jumping the gun here and talking about some of these ideas. But so let me talk about what's going on with what we're trying to do. But basically, we all know that in quantum mechanics you want to diagonalize the Hamiltonian, and that's one of the prime goals. And so let's think about a random Hamiltonian like the Anderson model. If you want to know something about the eigenfunctions, that means one way of doing that is to diagonalize the Hamiltonian and look at the eigenvectors. And in fact, so we're trying to develop a general technique for solving this kind of a problem, diagonalizing a Hamiltonian, especially a random Hamiltonian. And so I could talk about this in the context of the well-known localization problem, but really what we have in mind is many-body problems. So I'm going to go straight to a discussion of the idea of many-body localization. And what you'll see is that there's a nice interplay between perturbative ideas. When you're away from issues of resonance, perturbation theory works very well, and then you have to deal with more probability arguments, non-perturbative estimates, to deal with the possibility of resonance. And so this is sort of a multi-scale problem which borrows some of the general philosophy from the work over the last couple of decades on multi-scale RG and stat mech. So, in contrast to stat mech, what we're doing is basically doing approximate diagonalizations of the Hamiltonian. And of course, this isn't a new idea, doing a sequence or a flow of approximate diagonalizations. I've just put down a couple of references here, like the Brockett-Wegener flow. That's a continuous approach. Then there's similarity renormalization was discussed in Glasek and Wilson, where again basically you take H and you put e to the a on one side, e to the minus a, or do the similarity transformation, which is what we'll be doing as well. Also, block diagonalization methods have been used with good success for quasi-periodic Schrodinger operators by Eliason. But okay, let me go down to the basic start of the problem, which is we want to look at the idea of many-body localization. So let's put forth a many-body Hamiltonian and discuss some of these ideas in the context of it. So this is going to be a random Hamiltonian. So we see here we have a magnetic field, if you will, at each side of the lattice, H. And so we have this 2x2 matrix, so we have a spin at each side of the lattice. And then we have an off-diagonal term here, but then we've got a J prime, which is coupling different sites, nearest neighbors, let's say. And so since this term, this is not diagonal in the sigma z basis, this is going to be an off-diagonal perturbation of Hamiltonian. You could, if you will, go to a basis where each of these 2x2 matrices would be the diagonal, but then these matrices here would be off diagonal. So that's the point of view I want to take, where we start with the diagonal matrix, and then we have some perturbation on it, which is off diagonal, very general type of problem in quantum mechanics. How can we adjust the default basis in which you're working so that the overall Hamiltonian becomes diagonal? Okay, so and we're discussing localization. Now, everyone here, I'm sure, is familiar with the idea of localization in the context of the Anderson model. But let me just repeat it, just because it's a little bit non-trivial to understand what localization means in the context of the many-body problem. So, in fact, it took us quite a long time, maybe quite a few months, with some help from colleagues for us to get a grip on what many-body localization means. And you've got 5 minutes, so. All right, so in the Anderson model, localization means that the eigenfunctions resemble the ones where you turn off the off-diagonal part of the Hamiltonian. All right, so in other words, if you turn off the off-diagonal term, then the eigenfunctions are just delta functions at the sides of your box. Okay, when you turn on the interaction, they spread out a little bit. Basically, they resemble the j equals 0 eigenfunctions. All right, now, how can we translate this into the many-body context? Basically, the spin variables should resemble those of the j equals 0 states. Those are the states where you've turned off, again, this off-diagonal part of the Hamiltonian. So if we take j equals 0, actually j and j prime equals 0 for this discussion, so you have a prescribed set of 1s and minus 1s, spins up and spin down in the lattice. So in other words, we're going to call this the state labeling spin configuration sigma label. So in the one-body Anderson model, you specify your eigenfunction by identifying a site in the lattice. That's very easy to understand. In the many-body problem, however, you have to specify an eigenfunction. There's many more eigenfunctions. There's 2 to the n eigenfunctions. How do you specify it? You specify it by identifying a labeling spin configuration. All right, so now the actual interacting many-body wave function should be close, in some sense, to the label configuration. So if the label configuration tells us that we have, let's say, it looks like this, up, up, down. We have 3 sites in our lattice. The label says up, up, down. Now, the many-body eigenfunction will be very strongly concentrated on wave functions which have this as their leading term. That would be the notion of many-body localization. But you can go further than that, and note that this is also an issue of entanglement. Once you've got all these, when you have many-body localization, then you have approximate disentanglement of a spin over here and a spin over here. So there's some background here. This is a relatively recent concept which has been discussed in the literature, Lascaux, Leiner, and Altschuler. And then we've been talking a lot with David Hughes, who's written a lot about the way in which this is a transition from ergodic to non-ergodic situation. So just like in the ordinary Anderson model, is a transition between weak and strong randomness. In the strong randomness, you're going to have the localized situation where, like I described, the eigenfunctions resemble those of the j equals 0. But this goes along with short-range entanglement, as I just mentioned, and lack of thermalization. And the opposite phenomenon will be present in the case of weak randomness. By thermalized, we just mean that an eigenstate at a given energy would look locally like a statistical ensemble of states in thermal equilibrium, which would be the exact opposite of what the situation I was trying to describe, where you have really one state predominating for the localized regime. So there's this thing called the thermalization, eigenstate thermalization hypothesis, which is applicable to a more standard phenomena in many-body quantum stat mech, but which is not applicable when you have many-body localization. So we're interested in this transition, or at least one side of the transition, the localized side of this transition. Okay, so what type of result are we looking for? Well, like I said, we want to diagonalize the Hamiltonian with a set of eigenfunctions. We want to be able to have strong control over what these eigenfunctions are like. Analogous to the statement in ordinary Anderson model that you have exponential decay of eigenfunctions. So we obtain this by developing a graphical expansion with explicit bounds. Bounds not only on the size of the eigenfunction, but also on the probabilities that are relevant, because you're going to have, just as in ordinary Anderson model, you have resonant regions whose diameters are random. So the distance you need to go in order to obtain localization, exponential decay, is actually a random quantity. So you have to have good control probabilistically as well as quantitatively on the size of the eigenfunctions. Okay, so once you've obtained that, then you have, either because of the smallness or the rarity of the deviations from this label spin configuration, we want to show that after averaging over the labels and averaging over the randomness, the expectation of the, say, the spin at the origin in a given eigenfunction is close to 1. So which is, again, this is showing why would the eigenstate resemble the label configuration so that it had an absolute value close to 1. That's, again, this phenomenon of many-body localization. If it's resembling the label configuration, then it should be either +1 or -1, as the label is. And to give you an analogy from classical stat mech, where let's say you have a mixed state, one half of the plus Ising and one half of the minus Ising. Then you have a situation where if you take the mixed expectation of the spin at the origin, you get 0. But if you take the absolute value of either the plus or the minus expectation, you're going to get something close to 1. So what we're saying here is that this, in the strongly random regime, the many-body localized regime, we're basically in this situation where we have a kind of a pure state. Whereas the more common situation in many-body quantum mechanics problems is to have this thermalized situation where you have a mixture of all kinds of different states, which would lead to vanishing of the expectation, or the average of all these things. Okay, so there's your five minutes I've allocated to explaining this idea, and but I want to move on now and talk a little bit about some of the methods that we're going to be using to. Yeah, question?
So just to have intuition somehow.
Yeah.
In physics, the localization is more about the transfer treaty. I mean, you think about how, whether you can push the current through the system or not.
Yeah.
So is this somehow related to your notion of localization?
Well, that's one of the many things that go hand in hand with once you're able to show that the eigenstates resemble the label configuration, then along with that, you would expect a lack of transport. And so we understand in principle how to do that, but that's not like number one on our list of, of things to prove.
It's kind of a first crude step to understanding localization.
So we're just trying to get the simplest thing, which we know is definitely a harbinger of the transition between many-line localization and lack thereof. And but certainly you're right that there's also this transport issue, which should be addressed as well. All right, so to get us into this these techniques, I want to. When did I start? Was it like 10 after? Okay. So I want to generalize the Hamiltonian a little bit to get into the proper framework. We're going to start. We have a diagonal piece H0, and then we're going to have an off-diagonal piece, which is going to be a sum over connected subsets of the lattice, some j of x. So if you look at the Hamiltonian that I wrote down to begin with, you see here we have H0. This is diagonal if you change basis on side by side. And then you have this j prime term, which is off diagonal. It connects nearest neighbors in the lattice. But the point is that when we're going through this inductive procedure, we're going to be generating longer and longer range interactions. So this is useful to have this from the beginning. Okay, so as I said, so initially we have a nearest neighbor couplings in these j of x, but then as we proceed to get more and more interactions, the order in perturbation theory, in effect, connects with the range of the interaction. The more steps you make, the higher order you get perturbatively as a function of j. So since, as the title of the talk indicates, we're doing a kind of Newton's method scheme, which means we're going to go first order only in our perturbative scheme with respect to this parameter, these parameters j. So initially, j is just nearest neighbor. We're only looking at nearest neighbor interactions. But then as the procedure runs farther and farther, we get to higher and higher order effects, and we get longer and longer range interactions.
That's important to say, as the range gets bigger, the amplitude typically gets smaller.
Yeah. So as you know from Newton's method, you just work with first order perturbation theory to get your first guess, and then then you look at the how well you've solved your problem after adjusting for first order perturbation theory, and you find that the problem is much more close to being solved. In effect, these j's should be, after taking account of first order perturbation theory, then the effective j at that point should be the square of the one you started with.
John, one more question. So in 1D, as David Hughes perfectly knows, there's this asymptotically exact RG schemes based on eliminating of
Right.
bonds. Is it something close in spirit but an arbitrary dimension?
No, it's not that similar to that method. It's a nice method, but I'll show you what we're doing. Okay, so now, so you could say it's like a Newton's method scheme, but there's also these resonances to deal with. So you might say it's KM type scheme as well. All right, well, just to start off really simply, if you just have one site, then the eigenfunctions are going to be very closely resembling 1, 0, and 0, 1. These would be like the label spin configurations. Okay, so now the issue of resonance comes in. So perturbation theory, which is the approach we're going to be taking, works if there are gaps between eigenvalues. All right, so the problem is that as you get more and more sites in the lattice, as the volume gets large, the eigenvalues effectively become dense. And so you lose the gaps between eigenvalues. We all know this is a problem. However, at least initially, when we're just looking at nearest neighbor interactions, we can just define a criteria for resonance by looking at nearest neighbor bonds. And so when you make a transition which involves just these spins at the site I and site J, there's going to be an energy change involved in that. And you'll have a resonance if that energy change is close to zero. So we define some number epsilon, which is just defining how close two things have to be in order to be considered resonant. And if we're below this cutoff, we say that that link is a resonant bond. And we don't try to do perturbation theory when we're in the vicinity of these resonances. This is analogous to the situation if you're doing, let's say, RG in classical stat-mech problems. You have large field regions where perturbation theory is breaking down. You have to devise a different scheme to deal with those. And so these resonances are analogous to large field regions. The thing is, we have some randomness. These energies, at least at the first step of the procedure, are simply given by, they're split by the magnetic field. So in other words, the magnetic field, if you vary it at one site, it's going to increase the energy of the up state and decrease the energy of the down state. So as you vary it, you're going to cause splittings. And likewise, if you have something involving combination of the spin here and the spin here, as you vary the two magnetic fields, you're going to split the energies. The probabilities then that you have two spin configurations which are resonant is going to be small. Let's say you have a continuous distribution in the randomness. And if the probability of a resonance is small, then that means that these resonant bonds form a dilute set of regions where perturbation theory breaks down. So that's critical. Obviously, once these resonances start to percolate, then you're going to be moving over to this thermalized situation where you don't have many-body localization. Okay, but let's leave aside for a moment the resonant regions, and let's think about then doing first-order perturbation theory, Newton's method, if you will, in the non-resonant regions. So what we have to do, you see, is divide the off-diagonal elements of the Hamiltonian into the internal portions, which are within the resonant blocks, and external, which are not affected by the resonances. We only expand in the external links, Jij. Now let's define this matrix Aij, Jij over the change in energy. Then if you remember first-order perturbation theory, you define that new eigenfunctions, the perturbed eigenfunctions, is given by the unperturbed ones plus the sum of the interaction divided by EI minus EJ. And you can write this in matrix form as just saying that the new eigenfunctions are given by 1 plus A times the old ones. Okay, so that would be standard Rayleigh-Schrodinger perturbation theory. We're going to do something very close to that. We're going to, instead of using 1 plus Aij, we're going to use an exponential of A, which agrees to this in first order and has the additional nice property that it preserves unitarity, that preserves normalization of the eigenfunctions. So this then is the expression for the eigenfunctions, the Newton's method approximation, if you will, for the eigenfunctions, which exploits first-order perturbation theory. Corresponding to these eigenfunctions, you have a new Hamiltonian, which is obtained by the similarity transformation applied to H. Okay, so what exactly happens to the Hamiltonian? This is a little slide I want to go through. We need some basic properties of the renormalized Hamiltonian. But keep in mind that we know that in Newton's method, after accounting for first-order perturbation theory, then you would certainly expect that any remaining off-diagonal pieces in the Hamiltonian should be second or higher order. And so then that's, in fact, what we see when you, and this is a calculation to justify that. If you take the commutator of this matrix A with H0, then you get the E either on the right or on the left, and that cancels the denominator. That's why we have the energy denominator to begin with. And the result of this commutator is negative J external, the ones we're perturbing with respect to. And then now if you consider the commutator with the whole Hamiltonian, you get this negative J external plus the commutator of A with the interaction term. So what does this mean? When you do the similarity transformation on the Hamiltonian, you get a bunch of commutators. And we've just evaluated one of those. We find that we get a cancellation of the off-diagonal piece, just as we would expect. We have the original off-diagonal piece. It gets canceled with this negative term. And then you get a whole bunch of higher-order commutators. And if you work out the algebra, it's like this. But the main point is that you still have the internal links, the ones you didn't perturb with respect to, but all the other terms are higher order, at least second order, with respect to the original coupling. So, as I said, the external guys are gone. The internal guys remain because we didn't perturb with respect to them. The resonant regions haven't gone away. And J1 is going to be quadratic and higher order. And now it gets a little bit longer range, but it still maintains its locality properties because it all involves these multiple commutators of A with J, and both of those are really sum of local terms. Then, of course, we get a diagonal. There's going to be an energy change. There'll be a diagonal part of J1 can be absorbed into H0. And so we've got a new diagonal piece as well as a new off-diagonal piece. And then the eigenfunctions can be read off by looking at the columns of the basis change matrix omega. So then we want to continue the procedure a la Newton's method. Always perturbing in the off-diagonal part of H0, which at this point is O of J0 squared, but then, as you can imagine, after k steps, we're going to have this superconvergence. It's going to be J0 to the 2 to the k power. Okay, but we've kind of still have this issue of the resonant regions. And so they're going to cause some problems because these commutators are going to cause issues at the boundary of the resonant blocks. And since we didn't expand the off-diagonal pieces within a resonant block, it's going to continue to degenerate low-order terms, and it's going to spoil this nice superconvergence of the procedure. So as a result, we have to come up with something. How do we handle the resonant blocks? What you do is you just diagonalize, you do a block diagonalization procedure. If you combine H0 and the J internal within each of these resonant blocks, you of course know there has to be some matrix O which will diagonalize within that block. Now the thing is, you don't know very much about the matrix O. But the point is that you don't need to know very much about the matrix that diagonalized within a block, because after all, these blocks are known to be rare. And so we're willing to give up tight control of the eigenfunctions as long as we do so on a very dilute set of regions. All right, so, and certainly you're going to have entanglement. There's going to be a dilute set of regions where there is entanglement going on. But the point is that if you have one region over here and another region over here, this one and that one will be disentangled, even though within each of the resonant blocks you're going to have a lot of entanglement. All right, so once again we do a similarity transformation on H1. We call it now H1 prime. We've already done a similarity transformation to do perturbation theory, in effect, and now we're going to deal with the resonant regions with this matrix O. The upshot is there's no longer any J0 terms at all. And while there's some details which you probably don't want to hear about in a right now, but you have to also gradate these blocks in terms of how big they are, and you can only do these this type of rotation on the medium-sized blocks. The large ones you have to wait until the couplings get small enough.
So your statement will succeed to make the block transformation exact, the block normalization group?
Make the exact rotation within each of these resonant regions, yeah.
In the statistical mechanics, no one succeeded to do it except for exactly solvable problems.
Well, the thing is that maybe when you make that statement, you're thinking about doing a block, exact diagonalization, while saying something non-trivial about it, right?
Yes, and non-trivial to asymptotically to get to the fixed
So,
to identify.
I'm trying to separate the problem here. I'm doing a block diagonalization, but I'm saying nothing about it. Okay, so you can grant me that, I'm sure. The only thing that
you can build in correlations, you say.
The only thing that we need to know about is that these blocks are dilute.
Okay.
So there is an estimate that needs to be understood, which is why are these blocks rare? It needs to be done at each scale. But once we've got the rarity, I don't care what goes on within the block. Here's a little picture that give you an idea that there's these different scales. You have large blocks here, let's say, with these little links indicating that there's a resonance between the on those links. And then you may have some small blocks. These are the ones you can actually do the rotation on. And then you have longer links when you go to the second step of the procedure, where you have to look at next nearest neighbor links and understand what the criterion for resonance for second neighbors. In the third step, you would go look at resonances up to scale 4, and so on. So one way to think about the procedure then in the context of these resonant blocks is that we're doing quasi-degenerate perturbation theory. So it makes a certain amount of sense that if we're just doing ordinary perturbation theory away from the resonances, and in fact this is the standard prescription in rate of Schrodinger perturbation theory, when you have states in H0 which are very close in energy, you don't attempt to do perturbation. You first do an exact diagonalization within this model set of degenerate states. And then you can perturb in the connections between those states and the others. That's all standard first-year quantum procedure, and that's just what we're doing here, except that these blocks, of course, can be large or small. The number of states in a block of size 2 to the k is very large. So you're going to end up with sums over these states. But this is nicely matched up with the size of the couplings, which are j to the 2 to the k, as I mentioned earlier.
That J has to beat that be small enough to beat the 2 to the 2 to the k, right?
Well, yeah. Well, J has to be smaller than 2. Probably has to be smaller than
It has
maybe
to be smaller than half.
smaller than half, or maybe just to be on the safe side, 0.01. Likewise, you have energy denominators. Now, in the first step, I just said that the resonance occurs when you have I minus j less than epsilon. Now, we're going to be talking about longer range resonances, so we have to match the notion of resonance to the range of the interaction being considered. And so we let it be epsilon to the power I minus j. And so then this will match up nicely against the size of the coupling. If you have a coupling between I and j, it's going to have a corresponding order of perturbation theory. You have a certain number of links necessary to get from I to j. And so this is well matched up with that as long as j0 is considerably smaller than epsilon. You're in good shape. Now, again, we have I just want to give you a hint of some of the complications in our procedure, things that we have to deal with. When you have higher order diagrams, you have lots of energy denominators. And individually, they may be fine, but then you have to look at them in combination. So it's not simply just, j, ij over change in energy, but you've got, in high order perturbation theory, you've got tons of energy denominators, and all of them have to be controlled together. But that would maybe be a topic for a more technical discussion, which I could, those interested can contact me. Now, there is this issue here of how do we get control over the this inductive procedure. You might imagine that when you have an induction, you tend to lose a little bit in terms of your estimates every time you do a step of the induction. So you have to have some kind of global control over what's going on. And so you have to have something which goes a little bit beyond straight perturbation theory to keep the thing from spiraling out of control. And what we use, the main estimate we use is that if we take a graph that contributes to the basis change operator A, if we average it over H, we get a behavior something like this, where epsilon is this resonance cutoff. So J, some small number to the size of the graph. And the thing is that the average behavior then is much better than the worst case. The worst case, you would have A of G would be J over epsilon, because the energy denominator is known to be greater than epsilon. So then the worst case would be J over epsilon to the G. We see the average behavior then is only logarithmic in epsilon, whereas the worst case scenario is 1 over epsilon to the size of the graph. So this provides a way to do what you would call a Markov inequality, I guess, to say the probability that A is bigger than some number is bounded by the average behavior divided by that number. And so then we get a small probability involving epsilon for the probability of a resonance. So basically what this type of estimate gives is you have a sort of perturbative control over the size of graphs, ends up giving you non-perturbative control over probabilities, which is what we need to ensure that the resonant regions are dilute as we continue to the nth step of the procedure. Now, the other issue, which is a very important one, those of you who worked in the
Time's almost up. So.
Okay, yeah, this is my last slide. So, those of you who've worked in the standard Anderson localization problem know that the Wegner estimate is critical for doing rigorous work and understanding getting a handle on density of states, and ultimately to control the probability of resonances in your system. We have to devise some alternative to the Wegener procedure to understand the block-block resonances. These are the difficult ones. If I have a block over here on this board and another block over here on this board, how do I know that the probability of a resonance between them is small? What you do is you use the neighbors of this region. We make sure these regions are sufficiently separated, and then the neighbors of this region are well understood because they're non-resident, and they have a way of smoothing out the distribution of energies within this block. Okay, so I think that's a good place to stop, and I'm happy to take any questions if you have any.
I'm ready for one question, yes. Yeah, we only have one
Okay,
time. We're late.
so then very general question. So quantum mechanics is general can be represented as diagonalizing a certain matrix. So the question is, it could be single body, many body, any quantum mechanical system is a diagonalizing of the matrix. So
Yeah.
that the whole devil is what is the structure of the matrix. So then my question is, it looks like what we call many body differs from what we call one body, is that primarily that the size of the matrix is exponentially large compared to the number of non-zero elements. But that happens also on the Cayley tree. So my question is, do you know what, first, if there is any principal difference between the many-body localization in spin system that you consider and on the Cayley tree, just one single particle in disordered Cayley tree? And if there is, what do you think is in the structure of the many-body matrix compared to this matrix that corresponds to the Cayley tree?
Well, I guess I would. The short answer to that would be that I know why you're asking this question, because the Cayley tree is being used a lot as a model for many-body localization, and so yeah, I think that's a perfectly reasonable approach. Now, that being said, we're not working on the Cayley tree. We're working on real lattice. The main issue, as compared to, if you want to compare the many-body problem to the single-body problem, is that, as you said, the number of states growing exponentially with the size of the region, which gives rise to issues like I mentioned a little while ago. The sum over the states, sum over the 2 to the 2 to the k states is controlled by the size of the couplings. And this matchup of the number of states with the size of the coupling is completely different in the standard model. And that's really makes a distinction between the Anderson model and the many-body one. Now, if you take the a many-body problem on the Cayley tree, then yes, you'll have the same situation here. But if you take the standard Anderson model on the Cayley tree, you won't have this number of states.
So you think that it is simply the size of the Hilbert space that matters. So no other structure specific to many-body systems compared to Cayley tree.
Yeah, that would be my conclusion. Yeah.
Okay, I think we need to move on, so thanks very much for the question.